confirm that the audio is working before it's officially time to be doing math stuff. Oopsie. I had to mute myself on my second computer. I always forget that step. But that does prove the audio is working. Okay, as we've discussed on Piazza and people have been talking about in Slack, there was a little mishap with the most recent exam where T-Square mysteriously didn't want to export all the files. And we didn't catch it on the first pass, so we had to go back and grab a few extra files. And the TAs are scrambling to make sure they get graded so that everyone can get their grades back. So hopefully very soon. Kind of depends on getting a response from everyone. It's really hard to snag everybody in the middle of a week when they may already be super busy. But I think we have it under control. So hope for the best. But at this point, you should have started moving on to learning about Turing machines and a little more about languages and that kind of thing. The next exam will be on problem sets 10, 11, and 12. I think all three have been released publicly. I was only planning to focus on 10 and 11 tonight. More 10 than 11. Because the current plan is that there will be 2 more office hours prior to the next exam, which means you'll have more opportunities to ask questions about that. So just taking it from the top for the moment. This first question, I think probably most people will either be able to get it okay, or they'll be better off playing with it on Udacity to try to figure it out than trying to talk through it. Because if you haven't played with it very much yet, there's kind of a neat tool built into the Udacity site for the class where it can take in a set of functions for a Turing machine description, and then it'll actually attempt to emulate running the Turing machine and show you all the states along the way. And you don't even have to actually just do the problems that are in there. You could build entirely different things. The machine's meant to do entirely different stuff that those questions never considered. And it'll still spit out all the steps that things go through so that you can see what the machine is actually doing and how it behaves. Let's see, for question 2, I want to emphasize that this notation stuff, when you get to the exam, we're going to assume that you understand that. Like that 0 to the I thing, you are going to want to be able to look at that and know that it means 0 repeating I times. That is just the questions that are going to show up on the exam. I haven't seen them yet, but they always assume that you can understand this kind of notation. So if you don't feel confident that you can memorize it properly, or you just want to alleviate your, oh, geez. Sorry guys, Windows forced an update shortly before office hours, and now it's harassing me that it wants to reboot. But I didn't see the first harassing message until 5 minutes before, so I told it wasn't allowed, and now it might harass me all through our session. So that's kind of annoying. But anyway, if you just want to alleviate test anxiety or something, you're welcome to put what these things mean on your study sheet. We had that problem last time, Jamie. People said the screen looked blurry, and it turned out that it was just that their personal YouTube setting quality was set very low, but it was actually streaming at a reasonable quality. I should probably just start announcing a reminder for everyone to do that by default. There's like a little gear icon near the bottom right of the YouTube screen, and if you click that, it should give you a little menu that lets you decide what the streaming quality is. And if you turn it up, then the screen should look a lot more clear. Yeah, I should really just make it a note to remind everyone at the beginning of every session or something, because it seems like that's going to be a recurring problem with YouTube Live. I truly don't know why it does that. Any other thing that I stream from YouTube, it defaults to some reasonable level, but YouTube Live specifically, it's determined to believe that I have no bandwidth. Okay, let's see. Back to this question. Um, see, the question makes it clear that when it wants a formal definition, it wants the sort of mathematical looking definition where you define the Q and the sigma and everything. I would say if you don't think you'll remember what each of those are individually, that might be worth throwing into your notes too. I truly don't know that that's a thing that's going to show up on the exam. I haven't seen it, but it's a reasonable question to ask. So it's simple enough to take 2 lines of your study sheet to make sure that you don't forget that if you can't remember it, go for it. I mentioned it on Piazza, but also for this kind of question while you're doing it, I think it's worthwhile to say, okay, like this language is a string consisting of zeros, but only when the number of zeros is even is the string in the language. And then make yourself an example of something that's in the language and something that's not. That's good for clarifying your own ideas of how this language works. And once you've created the Turing machine, it's also good for trying to check yourself and say, okay, I'm going to pretend that the Turing machine is running on this specific input. Does it give me the output I expect? Does anyone have any questions about those particular languages before I dash along? I really wish we didn't have such a long delay. Okay, I'll double back if anyone decides to ask something. Same kind of reasoning goes in number 3. Make sure that you understand what the language is before you worry about how to build the Turing machine that's going to recognize it. W is very frequently used to represent a member of the set of words in a language. I don't know if that's mathematically wide or if it's just what Charlie and Chris prefer, but if you see a W in one of these questions, there's a pretty good chance that that's what it's meant to represent. And as the question says, if a question specifically says that you want a more implementation level, then you're kind of just describing what it does without going crazy trying to represent every single specific transition that could possibly be in the Turing machine. If you, for something where we ask you to give us all the transitions, it's going to be a pretty simple Turing machine, because I'm sure you can imagine what a nightmare it would be to try to grade something that consists of like 50 lines of different transitions. And what a nightmare it would be to try to put something like that together and properly debug it in the middle of an exam. So that kind of thing tends to be pretty simple. But something more like number 3 can have a much more complicated language with more constraints, because you don't have to deal with every possible teeny tiny detail. So there's a little more room to abstract some of the details away and make some progress. I think making progress on this particular question, when you're building your Turing machines, it's extremely useful to remember that you can cross things off as you go. I did not see the stream hiccup. I'm glad it's back. I'll double check the connection wires. Hopefully not bump anything too loudly. Okay, hopefully we're slightly better now. I checked the wires. Unfortunately, if local internet goes crazy, I have no control over that, but it's usually okay on weeknights. Anyway, for solving 10.3, your useful strategy is usually going to be something like remembering that you're free to cross things off on the Turing machine's tape. Like if you're trying to decide that you have an equal number of zeros and ones, you can do something like, I'll cross off a 0 and then go see if I can find a 1. If I can't find a 1 that matches that 0, then I know I reject. If I do find a 1, then I'll cross off the 1 and go find the next 0 and repeat. And just keep doing that process. And you lay it out in writing slightly more clearly than that, but that's the basic strategy that allows you to pull this off. And this is, we don't study this in this class, but this is what separates Turing machines from some slightly less powerful machines that can only look at their input but can't interact with it by putting stuff on a tape. So they wouldn't be able to recognize this type of language. That's just a bit of trivia, not super important for you to understand. See, 10.4 we did discuss briefly on Piazza. I didn't go into immense detail, but mostly I think intuitively most people are going to understand that most easily from the perspective of thinking about a computer program and how you can have infinitely many computer programs that do the same thing. Um, at the time I made comments, I was pointing out that you could add useless print statements or do completely pointless arithmetic, randomly calculate the value of a Fibonacci number or something in the middle of a program that does something else. And it's still an equivalent program from the perspective that it has the same output for a given input. Because for a Turing machine, that's all we care about. Like if two Turing machines accept the same things and reject the same things, then they're equivalent as far as we can tell. We don't go digging down into all the nitty gritty of how many states they have and that kind of thing when we're talking about machine equivalency. So that's why you can have infinitely many Turing machines that decide the same language. You can throw all kinds of garbage in there and have it still end up doing the same thing. Of course, when we create the official answer on Piazza, it'll be a little more formal, but I'm trying to give you the right intuition. Okay, so these last two, I think are more difficult to grasp, so I wanted to spend more time on them. So it says the remaining two problems will reinforce the notion that Turing machines are a robust model of computation. You can modify the Turing machine in many different ways while preserving the class of languages that can be decided by the model. This kind of thing, the reasoning here is important because understanding this kind of equivalence is important to being able to understand the later proof that Turing machines are equivalent to what a desktop computer can do. Obviously, a Turing machine is not going to be any fun to program if you wanted it to run a site like YouTube Live. That would be a nightmare. And the runtime would probably be a nightmare. But when the only thing you care about is whether a computer can do a thing or cannot do a thing, which is all that matters when we're in the computability section of the class, then they're equivalent. So this is a simpler version of proving that machines are equivalent than trying to deal with all the way up to the RAM model, which is the argument that shows up on Udacity. So this paragraph is very important. It tells you exactly what kind of strategy you're going to use to answer these questions. Usually what actually happens, like a simpler way of saying this is sort of like if you've ever heard the song, anything you can do, I can do better. Well, if you have two different types of machines with slightly different behaviors, and you prove that machine A can do everything that machine B can do, and then you separately prove that machine B can do everything machine A can do, then you've proven that the two are able to do all the same types of things, and that there isn't anything that one side can do that the other side can't handle. And that's what this is trying to get at. So let's talk about 10.5 a little bit. This is actually kind of similar to problem 4 from exam 3 in a sense. If you don't remember it, it was the extendable array problem. So you would have an array, and of course it has some slots in it. Doesn't matter how many. And the issue was that you had to handle your array in such a way that you could put new things on the front or new things on the back or do a lookup. And once you've calculated the amortized runtime, it would be constant time. So putting aside like the amortized stuff, one of the ways that people approached this problem when they were solving it on the exam was to say, I'm actually going to just cut my array in half. And I'm going to have one array that's the front and one array that's the back. And then I'll do a little bit of math to handle the indexes. But that way I don't have to worry about adding onto both sides of the array, and I simplify some things. This is kind of an inverse of the reasoning that's happening in problem 10.5. Problem 10.5 is taking a regular Turing machine where you would normally have an infinite tape going toward the right, and it's saying, well, what if we let the tape be infinite in both directions? Do we gain any computing power by doing that? And actually, probably the simplest way to argue that you don't gain any computing power there is to say, well, first, clearly this can emulate a regular Turing machine, because all you'd have to do is mark off what's going to be the beginning of the tape and ignore everything to the left and treat it as a tape that's only infinite to the right. And at that point, it's behaving exactly like a regular Turing machine. The hard part is going in the other direction and saying,